In this section, we continue our intuitive study of what the limit is by taking a deeper look at the limit of a function. We'll make it more formal at the end of this chapter, and we'll come up with limit laws that will allow us to calculate limits in the next section. But for now, we want to get a deeper, more intuitive feel of what a limit is. Without this crucial understanding of the limit, many topics in calculus will not make sense to you. So let me share my screen and we'll get started. Even though Sir Isaac Newton and Gottfried Leibniz came up with the idea of the limit and established calculus in the 1690s, the concept of the limit remained an intuitive one until the late 1800s when Augustin Cauchy came up with a formula to make it precise and calculable. We're going to stick with the intuitive idea until the end of this chapter, when we will make it precise using Cauchy's method. In this section, we're going to talk about the following topics. We're going to describe the notation used to indicate a limit. We're going to use tables of values to estimate the limit of a function or identify when it does not exist. And then we'll use a graph of a function to also estimate the limit or identify when it does not exist. As part of this work, we're going to have to define what we mean by a one-sided limit and a two-sided limit. And we'll look at multiple examples. Finally, we'll describe what we mean by an infinite limit, and in doing so, we'll be talking about vertical asymptotes. Let's go ahead and talk about the intuitive definition of a limit. We're going to do this by looking at several different graphs. We have the graph of x squared minus 4, all divided by x minus 2. We have the function, the absolute value of x minus 2, divided by the quantity x minus 2. And finally, the rational function 1 divided by the quantity x minus 2 squared. We're going to focus our attention on each of these graphs at what is happening around the point where x equals 2. Now let's take a look at the graphs. We're going to focus first on the graph on the left. If you look at this graph, you'll see it is a line, with the exception that when x equals 2, we have a hole in the graph, like a pothole in the road. The road continues on both sides, but at one point, the road is just missing. Now, notice that none of these three graphs is actually defined at x equal 2. In all three graphs, there is no y value for x equal 2. If all we said about the graph was that at x equal 2, the function does not exist, then we would lose a lot of information about the behavior of the graph near x equal 2. That would give the impression that these graphs are similar, and they're very, very different. What we're going to do now is we're going to talk about what the value of the limit is on the graph on the left. You can see right here that we have a hole at x equals 2. Now, what is the limit at that particular point? Well, when we're looking at the limit, we're talking about coming from the right side as the x values get closer and closer to 2 down here. X comes close to 2 from the right. What does it look like the function is going to hit for the y value? It does not care if the function value actually exists there. The idea is, what does it look like it's going to hit? Coming from the right is a one-sided limit, and it looks like it hits the y value at 4. Yep, 4. Got to count it out. Now, what about from the left, the other one-sided limit? If I'm approaching 2 from the left, the x values are getting closer to 2, 1.9, 1.99, 1.999, very close to 2. Then it looks like the y value is again 4. This gives us what we call the two-sided limit. It's the same from the right and the left. They both look like they're going to hit the same y value. That is the limit. The fact that we have a pothole right there in the graph at that point does not matter. It looks like it's going to hit 4 from both sides. So we say the limit as x approaches 2 of this function is 4. The notation that we use is the LIM, x getting close to 2. Notice we don't write equals. We use an arrow to indicate getting close to, but not equal to. And then we can either write f of x, or we can represent the function here. Either one would suffice. And the value of the limit is 4. It looks like it's going to hit 4. That's what the limit is. Now let's move on and talk about another type of function where the limit does exist, but the function also exists. This is called a displaced point. This does not actually appear in the textbook, so I added this into the lecture notes. We have a basic parabola here that's been shifted to the right 2. So the function is quantity x minus 2 squared. And when we're looking at the graph, notice divided by x minus 2. And notice that when we look at the graph, we have a pothole in the graph, but the point is actually defined up somewhere else. That means that this is a piecewise defined function. So we have 2 pieces. It either is the graph of x squared, x minus 2 quantity squared, as long as x is not equal to 2. And at x equal 2, it looks like the y value is 3. Now, this is a piecewise defined function. We have a pothole in the first part, but the second part tells us the function is defined there. There is a y value at that point. It's just displaced. It's not where we think it should be for the value of the limit. So on this problem, if I want to find the value of the limit as x approaches 2 of f of x, what do you think it's going to be? As I approach from the right side, the x values are getting close to 2, values like 2.1, 2.01, 2.001, and so on. It looks like the y value is going to be 1. Coming from the left side of the graph, it again, as we get close to 2, 1.9, 1.99, 1.999, it looks like the y value is going to be 1. The two sides agree, which means the two-sided limit, or the limit, exists, and it's 1. The fact that the function value, that f of 2 is actually equal to 3, does not affect the value of the limit. The limit is what it looks like it's going to hit. These first 2 types, the displaced point and the hole, are what we call removable discontinuities. They're breaks in the graph that could be fixed if we could just change one single point. We'll talk more about continuity in section 2.4. Now what we want to do is we want to focus on the middle one. Let's look at the center graph. The center graph is again a piecewise defined function, and it can also be written as the absolute value of x minus 2 divided by x minus 2. X cannot be 2, or we would have 0 in the denominator, so it is not defined at 2. We have open holes at each segment of the graph of the function. When we're looking at this, if I approach 2 from the right side, so here's 2, if I'm coming from this direction, and I trace my finger along the graph, it looks like it hits the y value of 1. If I'm approaching from the left side of 2, or as we say, from below 2, since the numbers are smaller than 2, it looks like on this piece that the y value is going to be -1. That means they don't agree. And because they don't agree, we say the limit does not exist. As x approaches 2 of g of x does not exist. And we write DNE. What we have here in the graph is what's called a jump. A jump discontinuity. In other words, I can't connect the two pieces of the graph. Even allowing that I could redefine one point, there's no way with one point I could connect the two pieces of the graph. This is not a removable discontinuity. It is not removable. There's nothing I can do to get those two sides together. The limit does not exist. Now what we want to do is consider the graph on the far right. This is the graph of 1 over quantity x minus 2 squared. When we look at the graph and we put our finger on the graph and we approach from the right side and we get closer values of x to 2, the y value seems to increase without bound. Without bound means there's no maximum value. In other words, it's going to infinity. On the left side, as I approach 2 from the left, it also looks like it's going to infinity. Now, infinity is not a finite real number. This means the limit does not exist. However, what we're going to write is we're going to write that the limit as x approaches 2 of h of x equals infinity. Why do we write that if that technically means the limit does not exist? Because it gives us information about the graph. This basically indicates that at x equal 2, we have a vertical asymptote, something that the graph gets very close to but cannot touch or cross over. And on both sides, the graph is going up without bound towards infinity. We'll see that this one is also what's called a not removable discontinuity. I can't define one point to fix this because the y values are going to infinity. One point will not connect the two halves. Now let's go ahead and think about what we've learned. When you think about the limit is not what the function value is truly. The limit is what does it look like it's going to be. This is sort of like playing with a Nerf gun and aiming at one particular thing. The limit is what you're aimed at. It doesn't matter if you don't even fire the gun. The limit is what you're aimed at. Maybe you fire the gun and it just kind of plunk right on the floor. Then the limit is still what you're aimed at, not where the bullet actually went. Maybe you aimed here, but it went there. Doesn't matter. The limit is what you're aimed at, what it looks like it would hit. Right? Let's now make this a little bit more formal. We're going to let f be a function defined at all values in an open interval containing a. In other words, on the number line, we have a, and I know that around a, it is defined. The function is defined there. However, at A itself, we don't know if it's defined. It might be, it might not be. That's the exception of A itself. We're going to let L, the limit value, be a real number. Remember, L is a y value. What the function gets close to as a y value as x approaches A. Then we say if all values of the function approach the real number L as the values of x, except at A, approach the number A, then we say the limit of f of x as x approaches A is L. In other words, as x gets closer and closer to A, the function y values get closer and closer and stay close to L. And we write this with the notation that you see here. Lim of x arrow A of f of x equals L. And we say it as the limit as x approaches A of f of x equals L. If the limit does not exist, on the other hand, then we write limit x approaches A of f of x equals D and E for does not exist, with the exception that if it goes to infinity or negative infinity, we'll write that while simultaneously knowing that means the limit does not exist. Let's now make it more formal when we talk about limits from the left and limits from the right. We can make the same definition that we did for the two-sided limit a second ago, but for values just coming from the left. This means that x is less than A, and it's approaching A from numbers that are less than A, below A, or to the left of A. And then as long as the function values get very, very close to L as x approaches A from the left side, we say the one-sided limit from the left exists. And we write the limit as x approaches A from the left of f of x equals L. Now notice in the notation here that we are using a negative symbol in the power notation to indicate that we are approaching A from the left side, from the negative side, right? Negative is to the left. So when we're thinking about that, that is the left side. So we write x approaches A in the power position, put a negative to indicate from the left. So what do you think you're going to put to indicate from the right side? And again, this situation here means that you have A here, we don't know what happens at A, and x is coming from that side, from the left. Of course, as you might imagine, when we do the limit from the right, we will put a plus sign. If you're talking about a one-sided limit, you must put either the plus or the minus in the power position above A. So we would write the limit from the right this way. Without a sign in the power position above A, it is assumed always that we're talking about the two-sided limit, that both sides agree and point to the same value. If they don't point to the same value, the limit does not exist. Now let's relate one-sided and two-sided limits. When do we have a two-sided limit that exists? Well, it makes sense if you think about some of the graphs that we had earlier, that the two-sided limit without a sign in the power position can only equal L if both one-sided limits exist and they're both the same number. So when we think about the graphs that we had earlier, right here, remember that the limit existed because coming from the right and coming from the left predicted the same y value. When coming from the right and coming from the left predict a different y value, the limit does not exist. In this graph, we could now write the limit as x approaches 2 from the right of g of x equals 1, and the limit as x approaches 2 from the left of g of x equals -1. These values are not the same, so the two-sided limit does not exist. In this case, both the one-sided limits agree to go to infinity, so technically they don't exist since that's not a real number, but we would write that both sides go to infinity. So again, when we're relating one-sided and two-sided limits, the two-sided limit exists if and only if the two one-sided limits exist and are equal. Now we want to talk a little bit more about what we mean by an infinite limit. An infinite limit is like our third example, where the y values are increasing without bounds. It generally means we have a vertical asymptote in the graph. Or if it happens at the end of a graph, it's called end behavior. Now, what I mean by end behavior is, let me sketch a graph for you right here. I have a parabola. If I look at the y values as x goes towards the right forever, the y values go up forever. This is called the limit at infinity. I would write the limit as x approaches infinity, meaning go right forever, of this function. What would the y value be? Well, if I call this function g of x, then the limit of g of x as x goes to infinity is infinity. That means the limit does not exist. We would call this an infinite limit because the limit value went to infinity, and we would call it a limit at infinity because x approached infinity. So this is an infinite limit at infinity. This is an infinite limit. It's not a limit at infinity because the x value is approaching 2. There are 3 types of infinite limits we want to take a look at here. The first one is infinite limits from the left. And that means as you're coming from the left, the graph y values go towards infinity forever. From the left requires the negative in the power position above a. This basically means that all of the y values are increasing without bound as we get close to a from numbers below a. If the values decrease without bound, as the values of x get close to a from the left, we say it goes to negative infinity. These are one-sided infinite limits. Again, it's approaching a finite value. They're not limits at infinity. What about infinite limits from the right? Same idea, but instead of the minus, you have the plus in the 2 positions. Is it possible to have a mixture? And the answer, of course, is yes, you can have a mixture. If you have a graph, you could have a vertical asymptote here and another one here. And let's suppose your graph comes up like this, and it goes down like this, and then it curves down forever, and then it comes out like this. If I were looking at the piece here on the left side, I would say that both one-sided limits go to positive infinity, and the two-sided limit goes to infinity. Technically, that means the limit does not exist. Infinity is not a finite real number. If I look at the vertical asymptote on the right, the limit from the right goes to positive infinity. The limit from the left goes to negative infinity. So what would I write for the two-sided limit without a sign in the power position? Of course, I would write D and E because they can't even agree on which way to go. One goes up, one goes down. Let's talk now about the two-sided infinite. We only write that the two-sided limit goes to infinity if both sides agree and they both go up. From both the left and the right, the y values increase without bound. We only write the two-sided limit approaches negative infinity if both sides agree and they both go down in the graph. So again, I can draw an example of this one here, where from both sides it goes up, and an example of this one here. This one goes down, this one goes down, goes down, goes down. Right? Again, we're only going to write that the two-sided limit approaches negative infinity if it approaches negative infinity on both sides of the location of the vertical asymptote. Still, that means it does not exist. Infinity is not a finite real number. Now let's talk about some problem-solving strategies. We're going to start with tables, and then we'll look at graphs. Tables, to my mind, are far more tedious, I guess is the right word, because they require a lot of computation. I prefer the graph method. However, we need to talk about both. So we're going to start with the table method. To evaluate the limit of a function f as x gets close to a, we begin by completing a table of functional values. We're going to choose two sets of x values, some to the left of a and some to the right of a, but very close to a. Now keep in mind that this is only an estimate, and we could be utterly wrong if we pick the wrong points. It can happen. Here's a sample table right here where you are filling out different values. So technically, you can do any values you want, but from a practical standpoint, we usually take the value of a, subtract 0.1, 0.01, 0.001, and so on, and then we add the same values. Right? Once we have our x values, we compute the function values on both sides of x equal a. And then we look at these values here as they get closer and closer to the value of x equal a, and we look to see if they look like they're getting close to the same number. And then we guess what that number is going to be. We can use a graphing calculator or software that helps us to graph these. If you have a graphing calculator, you can use the trace feature from the left or the right to watch the y values on the screen and see if they approach the same value as x gets closer to a. Let's go ahead and work this example right here. We have the limit as x approaches the value 1, which we cause a 0 in the denominator, so we know it's not defined there. There's a definite break in the graph. And the function is in the numerator, 1 divided by x minus 1, and in the denominator, x minus 1. We want to confirm this by graphing. But the first thing you might want to do is a little bit of algebra. Let's clean up this function and make it a little bit easier to compute. So we're starting with our function, and I don't like that complex fraction. A complex fraction is a fraction within a fraction. To fix that, I'm going to multiply by 1 in the form of x over x. That means that I'm going to distribute the x over each term in the numerator and over each term in the denominator. This would give me 1 minus x divided by x squared minus x. Okay? Now, when I'm looking at this, this eliminates the same two values. X cannot be 0 because of the 1 over x in the original, and x cannot be 1 because this would also give 0 in the denominator. This revised version of the function has the same two values that x is not allowed to be, 0 and 1. Now what I want you to do is go ahead and take that function and compute the function values as necessary, and then sort of see if, as they get close to 1, if they're approaching the same value. So go ahead and pause the video and then turn it back on and we'll compare our answers. All right. What did you come up with? Let's see. What I've done is I've actually added for you a Desmos graph. So if we click on the Desmos graph here, and I have already got it open, I'm going to turn it on. And you can see right here that this is the graph of that function that's up here. And then I inserted a table by clicking on the gear symbol and adding a table. I made the values match what I had in my table, so you can see the table values coming down here. Now, it's very hard on this graph to actually see all of these points. However, as I get closer and closer to 1 from both sides, it looks like the number is getting closer and closer and closer to -1. Let's blow up the graph in the vicinity of those points, which is right here, and see if we can see a little more detail. Again, these points are sitting right on top of each other. It's very hard to get them separated out. Keep scrolling. Can you see that these values are getting close to that point in the middle? And again, as we scroll in, we see that they are approaching that value. Now, Desmos has a bad habit of plotting straight across values where it does not exist. How do you know that it's not actually existing there? If you click on the exact point where x equals 1, it will tell you it's undefined. I think it would be better if it put a hole, but it doesn't. All right. Let's now take a look at the second example, which is z minus 1 over z squared divided by z squared times z plus 3. Again, I want you to complete the table or use technology in Desmos in order to do this. Pause the video, then turn it back on, and we'll compare. Let's see what we got. I also added this one into Desmos, and in this case, they're added in the same location. I simply need to turn them on by clicking on the circles. And I want to return my graph to the normal shape. So now you can see the shape of g of x. This is a rational function, the ratio of 2 polynomials. And this time, again, what we're looking at is the limit as x approaches 0. We want to know what's happening to the y values as x gets infinitesimally close to 0. So we start with -0.1, -0.01, getting close to 0 from the left. And then from the right, we start with 0.1, then 0.01, getting close to 0 from the right. Notice that these numbers, as we approach 0, are getting larger and larger and larger in absolute value, but they're all negative. In other words, from both sides, it looks like the graph is going towards -infinity. And when you look at the graph over here, as x approaches 0 from the right and from the left, you can see that indeed they are going towards -infinity. Let's now turn our attention to the problem-solving strategy of using the graph instead of a table. When we're looking at graphs, it's easier than using a table because you're not computing points. The difficulty is you have to have enough detail on the graph to be sure you're not missing something. In other words, you have to know how far you need to zoom in near the point to be sure you're seeing all the characteristics of the graph near x equals a. We're going to go ahead and use this method. We've been using it so far, And I want to go ahead and take a look at these right here. We'll work through these, a couple of them together, and then you can pause the video and we'll work them all out. When I'm looking at this right here, I have the limit as x approaches -11 of f of x. So I come to the x-axis, locate -11, and then I want to know, well, what's happening to the limit as x gets close to -11? What's happening to the function? From the right, it looks like it's going up forever. I can't even see it from the left. But if I'm basing this on this going up forever and ever and ever, it looks like from both sides, it goes to infinity. Okay? So on this one, we would write that this equals infinity. Now let's go ahead and take a look at the limit as x approaches -8. As x approaches -8, we have -8 down here. Notice that it is actually defined at this point here. We have a displaced point. We have a hole in the graph at this point, but it's actually defined up here at -3. But as we approach -8 from the left, it looks like it hits -6. And as we approach from the right, it looks like it hits -6. Both sides agree. That means the limit as we approach -8 equals -6. Now go ahead and pause the video, work out the rest, then turn the video back on and we'll compare our answers. So how'd you do? Take a moment, pause the video to compare all your answers to mine, and then turn the video back on because I want to talk a little bit more about this one up here in the upper left. Okay, one of the disadvantages of a graph is we can only see the part we can see. We can't predict what we can't see. We also can't get super accurate. I said the limit as x approaches 0 of the function is 1.25, but maybe it's 1.26 or 1.24 or even 1.3, although I don't think it's 1.3. I can't get that accurate. A table would give me a better idea of what the limit value actually is. I can get a good estimate from a graph, but it's not very precise unless I zoom in on that point. Let's talk more about the limit as x approaches -11. Now, some of you may instead have given the value of 4, which would also be an acceptable answer. What I assumed was happening at -11 was that it was going up on both sides of the graph towards infinity. Now, if it was going up on one side only, the two-sided limit would not exist, and I would need to write D and E. However, you could also have interpreted that particular limit as going up forever, like this, and passing up that value, so that at x equal -11, the y value is getting close to 4. So without knowing what the rest of the graph looks like, we don't know. It could have been infinity, does not exist, or 4. Let's just leave that one a great big question mark. This is the disadvantage of using a graph. Now we're going to move on to example 4. And example 4 is another rational function, 1 over x squared. We want to look at the graph as x gets close to 0 from the left, the right, and both sides to try to predict what the function value is. Go ahead and graph it or use Desmos in order to graph it for you. Let's now take a look. If I turn this one off and scroll down, I can turn on the next one. All right, and you can see this here. If I wanted to add a table of values, I would click on the gear symbol, and then I would click on the Create Table. In this case, I just want to look at the graph and I want to examine the behavior of the function as x approaches 0 from the left, from the right, from both sides. From the left, the y values are growing without bound. It goes to infinity. As I approach from the right, they grow without bound. It goes to infinity. The two-sided limit, we will say it goes to infinity, but technically that means it does not exist. So over here, we will write that the limit as x approaches 0 from the left of f of x equals infinity, but again, that means it does not exist, but don't give me that on an exam. And then we have the limit as x approaches 0 from the right, which also goes to infinity, which means it does not exist, but don't give me that on the exam. And then the two agree. So we would say that the two-sided limit as x approaches 0 with nothing in the power position is going to be infinity. All right, let's go ahead and move on now to another function and take a look at its graph. This is going to be the graph of 1 over x cubed. When I turn this graph off and turn on 1 over x cubed, pull it up a little bit, we want to examine the behavior of the graph as x gets close to 0 from both sides, the left, the right, and then both together. When we look at the graph of the function, though, notice that as we approach 0 from the left, it goes to negative infinity. As we approach 0 from the right, it goes to positive infinity. That's because this one is cubed. If you take a negative number and raise it to an odd power, you get a negative. But an or a positive raised to an odd power would give you a positive. In the previous problem, they both went up because no matter whether it's negative or positive, when you raise it to an even power, you get a positive. In this case, the two-sided limit, we will have to write d and e. From the left, it approaches negative infinity. From the right, it approaches infinity. The two-sided limit does not exist, and we don't write either one because they don't agree. Technically, all three do not exist. The next thing we want to talk about is this idea of how to predict the behavior of the graph. Remember that I said that its behavior near a vertical asymptote depends on the power on that particular part around the vertical asymptote value. If you have a function 1 over the quantity x minus a to the nth power, and n is an odd integer, it will go to negative infinity on the left and positive infinity on the right as you approach a. If n is an even integer, then it will approach positive infinity from both the left and the right. Technically, these limits do not exist. Yes, I keep repeating that, and I will keep repeating that until you've got it firmly in your head. The next thing we want to look at is how to draw a graph given some limit information. There is no one right answer here. There are infinitely many different ways to draw these. All I'm looking for are the key points. So let's take a look at this one right here. We want the limit of the function as x approaches 2 to be 1. That means that either it really is 1, the function is defined there, or I have a hole in the graph and it's not defined there, or it's defined there, but it's a displaced point. All three of those would establish that the limit as x approaches 2 is 1. Now, the next three pieces together, the limit as x approaches 4 from the left is 3, and as it approaches 4, same number, from the right is 6, and that at f of 4 it's not defined. That means I must have a jump in the graph. It's not going to infinity, so I don't have a vertical asymptote. But the two one-sided limits do not agree. One goes to one number, one goes to another number. So I must have a jump in the graph. Let's go ahead and produce some kind of graph that looks like that. I want the limit as x approaches 2 to be 1. So right here, I either want it defined there, I want a displaced point there, or I want a hole there. As the graph gets close to 4 from the left, I want it to approach the value of 3. But it can't be defined there, so I'll make it a hole. I'll just connect those 2 points with a straight line. Doesn't have to be straight, could wiggle, doesn't matter. As I approach 4 from the right, I wanted to approach the value of 6, but again, it's not defined there. This time, I'm just going to come in like this. Now, I also want the function defined over here so that I can get the limit at 1 to, or at 2 to exist and be the value of 1. Remember that the two-sided limit only exists if you can approach from both directions. And to do that, it has to be defined on the left side of 2. It doesn't have to go to infinity, but it could, right? Any kind of graph that meets these conditions would be acceptable. It doesn't have to look like the one I drew here, but it has to meet the primary conditions. Let's now take a look at this one. I want you to pause the video, sketch out a graph, and then we'll compare our answers. Your graph could look much, much different than mine, but the key pieces need to be the same. As x approaches negative infinity, end behavior to the far left, the graph approaches the y value of 2, which is a horizontal line. It's going to get closer and closer to 2 as it goes out. It's not actually required that it stay below 2. It could be above. It could actually oscillate above and below, but it's got to get closer and closer to 2 as it continues to the left. The last piece of information is that the y-intercept is negative 1/3. So I want to plot that point first. I made my ball a little bit too big. That's one. It should be a little bit higher than that. Then the next piece is that as f of x approaches, wrong piece. F of x approaches 3 from the left, it goes to negative infinity. But as it approaches 3 from the right, it goes to positive infinity. So at 3, I must have a vertical asymptote. From the left, it goes down forever, and from the right, it goes up forever. Then as x goes to the right side of the graph, a limit at infinity, the function value approaches 2 again. This one I drew coming below and then coming back up towards 2. Again, that's just fine. You could have also graphed something that came down like this and then oscillated as long as it got closer and closer and closer to the value of 2. It could also come down and approach from above. There are many ways, infinitely many ways to draw these graphs. There are 2 important limits that I want you to go ahead and memorize for this section. In the next section, we'll talk about why they have to be this way, and we'll talk about the limit laws and how to compute limits algebraically. For now, though, we're focusing on the table approach and the graphical approach. We're going to let A and C be 2 constant real values, like 5 and 7. The limit as x approaches a of the function x is the value of a. Now the function x is what's called the identity function. The identity function is the function that what you put in is what you get out. This is the function y equals x. If you put in 2, you get out 2. If you put in 5, you get out 5. If you put in pi, you get out pi. It is the graph that is its own inverse, both algebraically, graphically, and by reflecting across itself. So when we look at this particular function, and I want to approach the value of a, any a, let's suppose I set a to be 1 here. Then as I approach from the left and as I approach from the right, because the function is defined there and both one-sided limits exist and both point to the same value, which is the function value, I know that it is the function value there, which is just a. And what about a constant function? When we talk about a constant function, we're talking about a function whose equation is y equals c. When I'm looking at something like this, notice that the y value never changes. So if the y value never changes, it doesn't matter what a value x is getting close to, y is always c. This gives us two important limits that we'll use as building blocks in the next section. Now we want to take a look at one other type of graph. This is a type of graph. We've looked at jumps and we've looked at vertical asymptotes where the limits go to infinity, negative infinity, or 1 up, 1 down. But there are other occasions when a limit does not exist other than the jump and the infinite asymptote. This is primarily caused by oscillation. We want to take a look at the graph of sine of 1 over x as x approaches 0 from both sides. Since the argument to the sine function is 1 divided by x, we know that x cannot be 0, which means this function is not defined at 0. There's no solid point at 0. However, the sine function always oscillates between -1 and 1. As x gets closer to 0, it oscillates faster and faster. On a graphing calculator, this may just be a solid dark blob in the center of the graph. It is still a function. These curves do not intersect. They don't overlap. It's getting more and more frequent oscillations as x approaches 0 from both sides. It does not approach one single y value. It continues to bounce between -1 and 1 the closer you get. Because it never gets close to a single y value, we say that the limit does not exist due to oscillation. The last thing we want to do is take a look at that formula that we started out with in the last section. This is Einstein's formula proving that it is not possible to travel at the speed of light. Again, m is your mass at rest, or m naught is your mass at rest. M is your mass as you're moving. V is your velocity, and c is the speed that light travels. As the ratio of the speeds, v over c, approaches 1, that means that your velocity is approaching the speed of light. As these get closer together, we lead to something that results in 0 in the denominator. And because of that, that means that your mass is going to grow infinitely large. This is a positive value, and your mass at rest is a positive value. And as this gets smaller and smaller, closer and closer to 0, this is going to approach infinity. That means your mass becomes infinitely large as your velocity approaches the speed of light. In other words, I'm afraid there will be no warp speed and there will be no going from one planet to another in another solar system. In the next video, we'll be looking at limit laws. Limit laws are how to calculate limits algebraically. See you there.